starting? Yeah, because we don't have time. Right. So this is going to be the discussion of the mock test 9. Let me start the video. Okay. So let's try to discuss serial wise. Okay. So all of you know the questions, but still I will be writing them so that the way I say it maybe will also give you some ideas. So yeah. So let us begin. So this is mock 9. So this month and next month also, I think as much as we do, we will mostly be doing this kind of things. Okay. After that, when this batch passes, means goes out, then Raghav will be there and other people there. We will start new topic, and whoever is there, I mean, if you guys, and yeah, hopefully you will not be there. You will join somewhere. It's better. But either ways, yeah. Let's see. So this is mock 9, and so let's begin with problem number 1. So then we will start the new topics. Is what I was going to say. Okay. Here we will just try to add the finishing touches to the topics and some special topics and so on, like exam specific. Okay. So the question is there a polynomial px? Okay. Coefficients can be real or complex, which takes root 2 to root 3. Okay. So is there so does there exist? Does there exist? One second. Yeah, so I'm not sharing the screen. Okay. Yeah, I was sharing, but then I unshared, I think. Yeah. Right. So the question is, does there exist a polynomial px? And this could have even complex coefficients. So you see, we are really allowing for everything. Okay. Such that it takes root 2 to root 3. It takes root 2 to root 3. Okay. And it takes every other rational to rational. Okay. So this is a problem basically I came up with while solving some other question, and this was a failed attempt at some much different question. So let me see. So one person knows this a little bit now, but other people, what do you guys think? Are there anyone? Rasubro, have you seen this question? Good. Okay, then it's good. Very good. So what do you think? Do you think it is possible? Because I've not seen your attempt because other two people had submitted. So what do you think? So you think it's no. Okay. So everybody thinks it's no. That's clear, right? That there's no such polynomial. Because when you take polynomial combinations of root 2 and then it goes to root 3, it seems difficult for this to happen unless the coefficients are rational. I mean irrational. Yeah. Then you can certainly do, yeah. And then what does this mean? I think more than anything, this condition should tell you something. Yeah. So Chandan, can you, if you have thought more about this, and if it's taking rationals to rationals, really the key thing in the question was is that should be, what can we say about coefficients of from this condition? Otherwise, you cannot say anything. Okay, so then let me remove this. Yeah, the claim is that all the coefficients will be rational. That's very nice and very deep. That's how it should be, right? All coefficients are rational. And this is it, right? Once you do this, then there's nothing to do in the question. Then we are clear root 2 cannot go to root 3. So how do we prove that all the coefficients will be rational? Anyone? So you're trying to determine the coefficient from this input output information about the polynomial. So it's really a question about determining the coefficients. Like, you know what, not explicitly, there's nothing to determine really explicitly, but yeah, it's, if you are looking to find the coefficients given the values of the polynomial, you know, given points on the curve of the polynomial, how would you do it? Determining the coefficients or determining the polynomial. Come on. This should be sufficient hint. You are trying to determine coefficients from input output. From its, you know, values. Yes, certainly, right? And that's what it is all about. That, so let's do it. Let's just not means let's just write it. Okay. So if we, it's a very beautiful this thing. Okay, so in some sense, this is a core of many things that happen. This, and well, basically you can just take p of 1, right? And no, that's right, I agree with you. You mean after solving the equations, linear equation? Absolutely, absolutely right. That's right. That's right. That's what the thing is, right? So you're in any field. I mean, you're in, if you are in reals, if your coefficient, if your input output is from reals to reals, then your coefficients will also be reals, right? If your input output is in, let's say, if you know that for any input of a certain form, the output is also of a certain form, and the coefficients will also be of a certain form. You think, what does form even mean here? Okay, that's a question which you can ask yourself. And many variations of that have appeared in many places in different disguises. But no, greatest integer function cannot be written as a polynomial because it's not a, I mean, it's not continuous, right? A polynomial is continuous, right? Yeah. In an interval, it's, and in an interval, it is a polynomial because it's a constant function. Yeah, but that's a very, those are very interesting questions, what you are asking. Right. Yeah. I mean, yeah. That is clear. For greatest integer function, the answer is clear. I mean, yeah, I understand. In some intervals, it will not work. Some intervals will work, and yeah, and not at every point, but you cannot, right? Like at those boundary where the jump happens, you cannot give me any polynomial there, right? Around this point, you cannot define any polynomial because it's continuous, right? But in fact, every continuous function can be written in terms of polynomials, infinitely many polynomials. If you allow infinitely many polynomials, then any continuous function can be sort of in some way. But yeah, let's not go into that. So yeah. So this is the thing, and from these, but then what guarantees us that that this will be a solvable equation? I mean, why should, so you understand dot dot dot, I mean, why should this be solvable? Just because you have any equations, why should there exist solutions? You see, rigorously speaking, you have to explain this. Right? So there is a dot 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 here, remember? So m minus 1. Let's say I'm taking these values. You can take any values. But really, the question comes, right? Like, why is this solvable? And yeah, that is a, or you have to say, or you can try to say in some other way. Or maybe I should go till n, right? So this is not good, not correct. I can go till n. So, or maybe n plus 1, because there are, anyways, that's okay. If I'm starting from 1, then I should go to n plus 1. So I have n plus 1 equations. So these are all rational numbers. So you'll get a system of equations where the variables are the AIs. Remember that, right? The variables are your AIs. Okay? So the AIs, well, no. If you have n equations, then it can be really complicated, right? Yeah, I mean, and yeah, uh-huh, yeah. Right, right, right. And that is a standard exercise, right? That this is an invertible matrix. So if you guys have not done it, then try to do it. Yeah, that this is an invertible matrix, and this is just a separate question on its own. This is an invertible matrix. Okay, you can try to prove that. That means that you can solve the equation system, right? That there will be a unique solution, right? Because just think about a 3 by 3 case, right? I mean, if it's ax equal to y, then if a is invertible, then x is uniquely determined by this. Is that right? Yeah. So let me say this. So if you take the 3 by 3 case, then let's say there's a quadratic. So then you will have like a2 plus a1 plus a naught. So these are your variables. And this is something, c1. Then you have uh, so it should be 2 square, maybe 2 a naught, and this is c2. And then you can put 3 square, 2, right? Right. And you see, right? Then when you write it in that form, then this x is this a1, a2, a3. So the matrix that you will get will be 1, 1, 1, 2 square, 2, 1, 3 square, 3, 1, right? And this will be your a2, a1, a naught. And this is equal to this. And then if that is invertible, then right. And we know this, all these facts, that invertibility is determinant not zero and so on. But you see, that's a rather complicated reason, right? For something very simple. So try to give some other explanation as to why, if the co-rationals go to rationals, then the coefficients are rationals. Try to think of a better explanation. There is a much simpler explanation that you can give, or rather, yeah, without using determinants and n by n so on, right? Okay. So, but yeah, this is perfectly fine, but you can think of a better explanation, which doesn't use the things about determinants, because that fact about determinants is a little tricky to prove. If you prove it in full details, it's not straightforward, right? I mean, not tricky, that's theoretical. I think of a better explanation. Okay, so I've said some things, but now if I ask you, okay, so now the coefficients are rational, right? So root 2, so if you put in root 2 in the polynomial, you are going to get what? Some root 2 times, I mean, right? You get root 2 times some rational plus some other rational. Yeah, that should be fairly obvious. There's no way you can get root 3. So this is fine, but so the key thing really was about this. But now if I change the question, and this is something that you should think, and it's also, this has appeared in fact in exams, this particular thing. I mean, not directly like this, but they ask in some other way. If the naturals, or even if the not naturals, that will not be enough, I think. If the integers are going to integers, yeah. So obviously this question is solved, will be still solved, because that's all we used. So what can we say about the coefficients? Uh, yeah, but these are polynomials. You never know if something special can happen. I don't know, right? Because I mean, you have to think. I mean, these are not arbitrary system of equations, but yeah, you either give an example, counter example, or something like that. Yeah, then it's good. So let's think about this now, maybe then 5 minutes. Let's see, because otherwise maybe I don't know. So I get it. Yeah, rationals are not close. Integers are not close into division, but what can we? So if you strongly feel that it doesn't imply that obviously the coefficients are rationals, that's okay. That we have already seen, right? Because we only use integer values. But then you have to produce a example where integers go to integers, and or prove that integers go to integers imply coefficients are integers. This is a very interesting question, I think. But this is even there in some books. So I remember this is there in, I think this will be there in Niven and Zuckerman number theory book. And I've seen this. Once I remember discussing some Olympiad problems where a more complicated version of this was present with someone. Just think about this. I just drink some water and come. Okay, so now let's do it. Let's do it a little fast then. So, what do you guys think? Chandan, what do you think? Are you here? Yes. Okay, so you're thinking they are integers. Okay. Let's see. So no. So okay. Yeah, that may be empty. Why? I mean, so all of them could be not in non-integers. Oh, so you're saying p of 0 like that? Huh. So the one thing is clear that p of 0 has to be integer, right? So a naught has to be an integer. Yeah. You mean just the expanded form a and x? Okay. Uh, what is yeah? This is px. Yeah. So we can actually just forget the last one, right? Maybe one can say that we can take x common. Okay. No, wait. Let's see. No. So whenever you put in an x, this product is an integer, but it doesn't mean that this has to be. It doesn't imply that this is integer. This is not does not imply. You understand, right? Like rationals could cancel with. Still, yeah, I understand. So now putting it like that, one may change that. One may think that yeah, it can be rational. It can be should be integers, but p of 1, yeah. Hmm. Even terms or something like that, right? Right. Hmm. Uh-huh. No, but where do we get all the natural numbers? It's 2 into this, right? Yeah, but you see, 2 into this is an integer. That does not mean that this is an integer, right? But then the values are also changing, right? Right. I mean, you understand, right? The values are also changing. That is the problem. Like here again, you will get, but the value is also big. So you can get new primes and new things in the denominator, or rather new factor. So let's see, right? So what do we get in the numerator? Let's see. So we get, um, so we get, yeah, but, right. You see, you get 2 into this a naught, right? What do you get here? 2 square a2, a4, and so on. But then how? So yeah. So then what do you say? Oh, yeah, coefficients, right? Yeah, right, coefficients. So each time you're saying they have to divide. Uh, no, they have to divide. No, really, that's not. No, but you see, this is the sum is also here, right? Sum can mix things, and you don't know how it can change things, right? I mean, it's a summation of things, right? I mean, some irreducible fractions can always become an integer, right? You must have seen questions like, I don't know, like 1 by n1, 1 by n2 equal to some integer, and you solve it and so on, right? Some other, you understand, right? These things are possible, and it's much more than that. There are even things on the top. Okay. Then that's, yeah, let's say then. So that is the most natural counter example, or plus, yeah, or even you can take minus, it doesn't matter, right? And the thing about these things that this is x choose 2 or x plus 1 choose 2, if what you were saying, right? And these kind of things, these are the canonical examples, right? It will take integers to integers, it's a combinatorial thing, but its coefficients are not integers. So now you have all examples. That's what this is. And similarly, you see, so you can give so many examples, right? You can get pi, or rather, so this is the thing. You see, these things can happen. So I don't know. I don't know. This is what happens. Uh, so what was I saying? Yeah, that this is x minus 1, x minus k plus 1 by k factorial. What can you do? These are rationals. Yeah, these are x. This is x choose k. You put any integers, either it is 0. I mean, after I don't know. So what happens? Yeah. So this is, I mean, if the numbers are small, then this is 0. From 0 to k, it is 0. Beyond that, it is an integer, but its coefficients are not, right? So that's the thing about these polynomials. These are very good. So if you look at this book, Niven and Zuckerman, number theory, then there is a chapter on binomial coefficients. I think this will be there in that chapter. Binomial coefficients, and these are called integer valued polynomials. These are integer valued polynomials. They return integers, right? Then the input is integer. Now the question can be, find all such polynomials. That's homework. It's not a hard problem actually. Find all such polynomials. And it's all these three problems that we kind of did. This third problem will be connected with the first problem, and as far as I can, as in the way I see it. But you treat it as a problem and try. It's not some theoretical big thing. Okay, it's a problem. It's a, it's a, you can see. I think this was the problem that I was discussing once. Find all such polynomials. Okay. All right. So this is the thing. Yeah. The next variant of this that can be tried is rather wonderful again. Is if p of q. Okay. So I don't know actually. I shouldn't say. I was no. So if p of q is inside z, right? So I don't know. I'll try this. Then does it imply that the coefficients are integers? No, because all rationals are going inside integers. Sorry? So it will not, I think. And in fact, is there even any polynomial that does this? That is, that even seems wrong, right? So this is the good question. Okay, so maybe this at this point, so what happens is when you say that P of Q goes to Q, then there is a whole, this is basically all of QX is what we have proved. All polynomials are rational coefficients. When you say that, when you put a rather more strict condition, then as I've asked, find all such polynomials, so they are more easily describable. They are a subset. But when you put more harsh condition, then maybe this set becomes empty. I think, let's say you can try this. This, yes, yes. Mm-hmm. Okay. Uh-huh. Why? No, so you have to say something like after a certain point it is monotonic and there it will, this will happen. Right. You're not wrong, but if you say this just initially, then it might be wrong, right? Yeah, but after a certain, but if you say all that, and that's something that you know that after a certain point it is injective, and formally speaking, we have also discussed it. So yes, so dot dot dot, no polynomials, right? Is was that your conclusion? Yeah, and so if others, if you're not clear, think about, just try to think, mean just write it now. It's, so you try this. So this is simple, but it's okay, fine. Yeah, this is just, yeah, this is simple. Okay, this is rather silly maybe. Okay, so you see, not always we get good questions. Okay, so let's move to the second question then. Um, yeah, and here the question is there, so is there a continuous function? So now I'm allowing for more, right? I'm allowing for a continuous function that can do this. Yeah. So this maybe is, I should have said this is part 2 of the same problem, right? So this is question 2. Let me write this here. 9. Yeah. Let's write it in full. Okay. Is there a continuous? So I suggest you guys can go back and look at this section in Niven and Zuckerman on binomial coefficients. It's a very good chapter. There are a lot of small gems here and there. Okay. If you get it stuck at some double star question, then don't spend too much time on it. But or triple star, I don't know the standard. You can see, I forgot it. But you will. It was a very good experience for me when I was solving it. Okay. So yeah, is there a continuous function? Yeah. R to R that takes rationals to rationals and takes root 2 to root 3. So now it's a continuous function. So it's not a polynomial function. It's a continuous function. This way you can gain intuition about things also. So we learn a lot of things from this. No, that is That also is possible if this is possible, because see, I want to say one thing here, which I have repeatedly said while discussing calculus analysis and so on, that see, polynomials are algebra, right? And algebra distinguishes root 2 and root 3, right? For algebra, root 2 and root 3 are different things. Because what is root 2? Root 2 is the smallest degree polynomial that uh, I mean, so what is root 2? Root 2 can just be seen as the roots of the polynomial x square minus 2, right? That's the definition of root 2. And then similar definition of root 3. The root 3 is there. But then you see root 2 and root 3 are different, right? They're coming from different polynomials, different origin. Similarly, E and root 2 are completely different algebraically, because E satisfies no polynomials, at least. Yeah, it is as a fact we know. So in algebra, so when algebraic things are there like polynomials or such, then different rationals are distinguished. Like the smallest degree polynomial that root 2 satisfies is different from the smallest degree polynomial that root of root 2 plus 1, root of root 2 plus 1 will satisfy. Yeah. So in that case, those numbers are different. But continuous functions are analysis, right? Continuous functions are analysis, open sets, and those kind of things, intervals and such. And analysis does not distinguish root 2 from root 3. Analysis does not distinguish pi from e. For analysis, both pi and e are numbers which are not rationals, right? Because what does analysis do? You start with rationals, and then in one shot, everything else is constructed, right? We want to have every set to have a supremum, and those numbers are defined as supremums of the rationals, subsets of rationals, and we get every number in that way, because we want them, because we want supremums, and so everything else has equal status. So that is all I'm trying to say. That in an analysis, it's not they don't have different status. Okay, but that doesn't answer this question. But I mean, that was what I had in mind. I thought, so I knew the answer is yes. Then it was just a matter of making it. Okay. So anyone has any ideas? So the answer to this is yes. But what I have said doesn't explain that. I'm not saying it explains it. Okay. So that maybe just helped me to just frame the question. Because first I came to the polynomial thing, but then I said I can do it for I knew it was possible, and then I eventually it was possible. So basically the point is you want every rational to go to rational. Yeah, you want every rational to go to rational, and you want root 2 to go to root 3. So I'll make it graphically. This maybe will be a new technique. I do remember vaguely discussing this kind of thing earlier at some point. Like can a continuous function take some value even number of times, and those kind of questions. But yeah, this is maybe a little tricky. So, but maybe you guys would have maybe thought of some different ways. So it's possible, would have been possible. So what I want is so let's take a, so I will give some of the construction. Okay. And meanwhile, I'll ask some questions in between. So the idea is that, see, this is root 2 and this is going to root 3. But other rationals should go to rationals. Okay. So here is the first thing. Let me just make the construction from 1 to 2. The rest will be homework for you guys. Out to work it outside, continuously extend it outside will be, that's not difficult. And I will also ensure that this 1 goes to 1. Hopefully I can ensure it. And this 2 goes to 2. So 2 is not very far, goes to 2. Okay. So I will make a function inside here somehow that will take rationals to rationals in a very logical way. Takes rationals to rationals and takes root 2 to root 3. Can you make it outside? So outside, how you will make, because outside there are really no conditions. Yeah, you have to just extend it continuously outside so that you can think. But let's not think about it now. Let's invest our energies in understanding and answering the details of this construction. Okay, so once again, make sure that I want root 2 to go to root 3. Okay, and my 1 will go to 1. So let's just focus on 1 to root 2 for now. Portion from 1 to root 2. So any ideas how I can make a continuous function that goes from root 2 to root 3, but it takes every rational in between to a rational height? Any ideas how we can ensure this? Yeah, I want the rational. Now you know that it's possible. I am telling you that it is possible. Okay. Okay. Let's see if there is any flaw. Then tell me. Then we'll see. But I want every rational to go to rational, and yet I want root 2 to tend to root 3 somehow. No ideas. Okay. So fine. Good. No problem. That's not a problem. I'll give you another. Maybe let me say a word. Let me. If I tell you that I'm going to make a piecewise is what I have in mind, and these are the key. Piecewise linear. I'm going to make something which is piecewise linear. Now, that may also not help, or does it help? But somehow it will be broken lines that will somehow converge to root 3. And see, if you have broken lines, and all you need to care about is the endpoints, right? If the endpoints of a line are rational, I mean, if they take rational endpoints, and if they take it to rationals, then everything in between the rationals will go to rationals. Do you guys agree? If you have rational endpoints and they go to rationals, and the line in between will also take rational endpoints to rationals to rationals. That's clear, right? Rational slope, then everything is good. So I want these rational endpoints. Yeah. Rational endpoints. So is everybody following, right? I'll take rational endpoints and I'll send them to rationals. And I'll join in between, between those endpoints, I'll join them. I'll just make lines. Right. So this could be a point, and this could be these two rational points. I'll send them to these two rational points, some rational points, and I'll just make a line in between. Another rational, I'll send to another rational. Another rational, I'll send to another rational. Rational here, I'll send to rational here. And in between, the definition will just be line. So piecewise defined function and piecewise linear, in fact. So are you guys following the idea? Yeah, Chandan and Rasubro, yeah, Raghav. Is the idea coming? Or yeah, I mean, so what would you need? So basically, see, now what is the decision we need to make? The decision we need to make is how will you define the blue points? Am I right? I mean the bottom blue points on the x-axis and the blue points where you're going to send them. Is that right? That's the only decision. Yeah, but the root 3, but also the input matters, right? Because then only we can ensure that the green portions in between, everything is, is coming from rationals as taking rationals. Right. So you see the input endpoints and the output endpoints both matter. Okay. I mean, that's in the graph, that's, I mean, the blue point above captures both of them, right? So that's the thing. So is it clear then, right, that we just need to worry about some blue points? I mean, maybe infinitely many, obviously, blue points that are going to root 2, and they are rationals, and their outputs should also be rationals, and they are going to root 3. That's all we need, right? Then the lines can be defined in between. Is this okay, Chandan? Is this idea fine? Right? So you just need these rationals, x1, x2, x3, some rationals, and they should tend to root 2. And there here you need the heights to be again rationals which tend to root 3. And that's it. But can't we provide such a sequence? Obviously we can, right? Just take 1, yeah, 1, yeah, 1.14, 1.141, and just take the expansion. And then just send it to the corresponding decimal expansion of root. Even so, non-theoretically also, just whatever it, I don't know, maybe 3 or something. That's it. And in between you define it by lines. Yeah, so between, so you'll say this is the ith partition, I plus 1th partition. You write it in that, it will be that line, equation of that line, so on, so on. And now it is clear also that it's going to converge to root 2. Root 2 will go to root 3, so it will be continuous. Root 2 will end up going to root 3. So, but you have to try to prove the continuity. So write the definition clearly, prove the continuity. From the right side also you have to do that and say, focus on the left only, right side, even if you write by symmetry, it will be accepted, I think. So, and then complete this also somehow. Yeah. Isn't it a very beautiful question, right? It just, I think, very nice, and it's, yeah, very, yeah, it comes. Okay. So it's not root 2 or root 3, right? You guys see the difference, right? What happens in your polynomials? I mean, this should be f, not p, but this is what I want to say. Okay. Right. So what does this solve? This gives us a remarkable solution, right? This tells us that, you see, for every irrational number, for any irrational number x, rather you fix, not just irrational, right? I mean, you just fix it, right? You just fix 1, and you can send it to any real number. You can fix the, or maybe not 1, because the rationals are going to rationals. So you take root 2, and you can send it to any real number, and you can get a continuous function. And yet this continuous function is taking rationals to rationals. What is the last consequence of this? That there are as many continuous functions which take rationals to rationals as there are real numbers. For every real number x naught, or rather y naught, for every real number y naught, I'm able to define a continuous function like this, right? That takes root 2 to y naught. So there will be different continuous function for different y naught. Yet it takes rationals to rationals. So the number of continuous functions that takes rationals to rationals is equal to the size of R. I mean, that's just not useful, not very useful. Yeah. Okay. In fact, the set of all, so let's not get into that. Okay. Yeah. Is the set of all continuous functions. So I knew this. So is the set of all continuous functions? Yeah, that should also be. Yeah, that is also countable. And that is also R size. Okay, no problem. So this is what we discussed. Okay, so fill in these details. Okay, and the problem I've given. So now we can see. Should we move? Let's not go to the next question. Okay, that's fine. Yeah, let's keep these 2 questions, and next time we can go a little faster. These 3 questions. Oh no. So question number 3 is different. That's like more like matrix manipulations. 4 and 5 are different. It is not what it looks like. Okay, 4 is combinatorics. 5 is a little bit of a game theory. It's games. It's a game. So, and it's a very combinatorial game. Just written it like this. Just written like that. So are there any questions? Otherwise, I'll end early today. Yeah, it's very late. You can do it for uncountably. You can do it for at least countably many. Yeah, you can certainly do for, you can see, right? You can do it for any number of points, because you can take small intervals, right? If there are at least on a discrete set, you can do root 2 to root 3, root 3 to root 4, root 4 to root 5. That also you can construct. And yeah, very interesting things, right? And what will be, and these are the functions that are eventually eventually when you study these better and better, then you will get examples of functions which are continuous everywhere but not differentiable anywhere, not even one place, and many more interesting examples. Okay, but for now this is good construction for us and things to learn, relevant thing, not very relevant.